This is the start of a series of 4 videos about acids and bases that will sort of give us a good introduction to acids and bases, which can be a complicated subject. And so we won't go into it in a great deal of depth, but it'll give us a good foundation in case you need to study acids and bases later on in a more advanced class. First of all, let's talk just briefly about some properties that acids and bases have. Acids tend to be sour if you taste them. Bases, if you can taste them, tend to be bitter. Lots of bases are poisons, and so I think our ability to taste bitterness is a kind of a warning that's built into our physiology to keep us from eating something that could harm us. Also, bases tend to be slippery. So if you get a base on your fingers and rub it around, you can definitely tell that there's something slick there. So those are a few general properties of acids and bases. But now let's define formally what are acids and bases. The first person who really came up with a good definition for what an acid is and what a base is was a guy named Svante Arrhenius. Svante Arrhenius was a Swedish chemist, and his idea was acids give hydronium ions, which are H3O1+ ions, in aqueous solutions or in water-based solutions. Now, very often chemists are going to simplify hydronium ion to H+ ion. So an example of an acid would be something like HI. HI, when you put it in water, will actually react with the water and it will produce hydronium ions, H3O+, and iodine ions. That's actually what's happening in reality. But chemists will often model that process as HI just decomposing or falling apart, sort of ionizing into H pluses and I minuses. So H plus and H3O plus are often used interchangeably by chemists, and in calculations they will always come out to be the same values. According to Arrhenius, bases were something that produced OH minus ions or hydroxide ions in aqueous solution. An example of that would be sodium hydroxide. NaOH, when you dissolve it in water, splits up, dissociates, and it gives you Na plus OH minus. So because it produces OH minus in solution, Arrhenius would have called that a base. Another model of acid-base chemistry was provided by Bronsted and Lowry, two chemists that were working independently and came up with this idea. An acid, they thought, was something that would donate a proton, or an H+ ion, in a chemical reaction. A base was just the opposite. That would be a proton acceptor in a chemical reaction. So what this did was eliminate the need for aqueous solution to even be present at all, and it expanded the definitions of what could be called an acid and what could be called a base. So in this reaction, NH3 plus HCl, forming ammonium, NH4 1+, and chloride ion, it's clear to see what's the acid and what's the base. Because the ammonia accepted a proton and became NH4+, it was the base. Because the hydrochloric acid donated that proton to make NH4+, it is the acid. Now, after the reaction occurs, we have a different acid and a different base, actually. NH4+ could donate a proton because it has an extra one now. And Cl- would be attracted to H pluses and could potentially be thought of as a base. This is the idea of conjugate acid-base pairs. Conjugate pairs exist in acid-base reactions like this one. If you put acetic acid, HC2H3O2, in water, it will ionize to produce the hydronium ion, H3O1+, and the acetate ion, C2H3O2, 1-. Acetic acid is, of course, an acid. But weak acids, which is what acetic acid is, and we'll talk more about what makes an acid weak or strong later on, become conjugate bases in acid-base neutralization reactions. So this acid is a conjugate of this base, the acetate ion. It's a proton donor, but this base could function as a proton acceptor. So this is called the conjugate base of acetic acid. Water is functioning as a base because it accepted the proton here. So we don't think of water as being acid or a base, but it is in this reaction. And because it formed H3O+, which could be a proton donor, that is a conjugate acid. So in every acid-base neutralization reaction, there's an acid and a base, and then there's a conjugate acid and a conjugate base. We can tell them apart this way. The conjugate acid has one more proton than the conjugate base, and of course the conjugate base has one less proton, and that also affects their charge. Let's look at some examples. Can you identify the conjugate pairs here? If I look at HCO3- and H2CO3, they differ only by the presence of a proton. H2CO3 has one more step positive charge, that's because of the additional proton, and you can also see the presence of the proton in the subscript of 2 compared with the subscript of 1 in HCO3 1-. So this is an acid. It's a conjugate acid, and this was a base. If you look at H2PO4- and HPO4-2-, this has one more proton, so it's the acid, and this has one less proton, so it's the conjugate base. What are the conjugate bases of these four? Stop the video, see if you can come up with the formula for the conjugate base, and then I'll bring you solutions in a little bit. So HI, if I take a proton away, I will have just I, because H is the proton. And protons are 1+ in charge, so what I'm left with is I1-. H3PO4, conjugate base would be H2PO4, one less proton, and then it's one step minus. NH4 1+, NH3 one less proton, and from plus it goes down one step to neutral. H2O, well, this is a kind of a tough one, but if you visualize H2O as HOH and take away that proton, what you're left with is OH, and of course you lose one step of charge as well, so OH- is the conjugate base. Identify the conjugate acids here. Stop the video and do your best to identify what the conjugate acids would be, and then I'll give you an answer in a little bit. Well, if I add a proton to H2O, here's what I get. H3O. I'm added one more H. And of course, protons are positive, so I have to make the charge go up by one step, H3O+. SO4-2- HSO4 1- is the conjugate acid. HPO4-2- H2PO4 1- would be the conjugate acid. And PO4-3- HPO4 2- would be the conjugate acid. You might have noticed here that HPO4-2- is a conjugate acid of PO4-3-, but it's the conjugate base of H2PO4 1-. This same substance can function as an acid or a base, and it will function as either one depending on the situation, depending on what else is there in solution. Substances like that are called amphoteric substances. They can function as an acid or a base depending on the situation. Earlier I referred to something as a weak acid. Here's what it means for acid to be strong, and later we'll talk about what it means to be weak. Strong acids ionize completely in aqueous solution. That means when you put a molecule that's a strong acid in water, none of the molecule remains. Every molecule will split up into ions, or will react with water to produce hydronium ions. So an example of a strong acid is hydrochloric acid. This is a well-known strong acid, HCl. When I put HCl, which is a gas, into water, it not only dissolves and splits up the individual molecules into solution, but the molecules themselves ionize and give you H+ and Cl-. This is just a model of what happens. Of course, hydronium ion is really produced. The key here is that this is a one-way arrow. Every molecule of HCl gives a H+ and a Cl-. There are none of these left after the thing has a chance to dissolve. It's important to know what the strong acids are, and fortunately it's not a very long list. There are only 6 strong acids. One that we just looked at is hydrochloric acid, HCl. That ionizes completely to give you H pluses and Cl minuses. Another one is sulfuric acid, H2SO4. This is an example of what we call a diprotic acid, di for 2 protons. This will split up completely to give you 2 protons, 2 H pluses, and SO4, which has a 2 minus charge. Nitric acid is our third strong acid, HNO3, which will completely split up to give you H plus and NO3, 1 minus. That's a monoprotic, a single proton acid. Hydrobromic acid, HBr, will split up completely to give you H pluses and Br minus. Hydriodic acid is HI, which will split up to give H plus I minus, and this will completely ionize. Perchloric acid is HClO4, and HClO4 will split up completely to give you H plus and the perchlorate ion, ClO4, 1 minus. Weak acids don't do that. Weak acids ionize incompletely in aqueous solutions. So an example of that would be hydrofluoric acid. It's an acid, it's a proton donor, but when you put it in water, it doesn't completely dissociate. It starts to, and you will get some H pluses and you'll get some F minuses. But this reaches an equilibrium, and so the forward reaction that produces the ions is going at the same speed as the backwards reaction that's making the ions turn back into molecules. And in fact, very few HFs really ionize. So there won't be much of this in solution. Mostly this is what you'd have in solution. If you were to look with submicroscopic eyes so that you could see the individual ions and molecules in solution, this would be the difference between what you'd see with a strong acid and what you'd see with a weak acid. In the strong acid, all of the individual H's exist as protons, H pluses, in solution. And all of the anions, like maybe this is HCl, would exist as individual Cl minuses, and you would not find any HCl molecules. They just wouldn't be there. In terms of a bar graph, when you start out with a strong acid, all the molecules you have in solution would be HAs. But as soon as they dissolve, you have no HAs. This is a bar graph for HA, but it's 0. And you have many H pluses and many A minuses. Every molecule has converted into ions. A weak acid, on the other hand, you start out with HB, which is going to be our weak base, and by the time you reach equilibrium, so that the forward and backward reactions are happening at the same rate, you have very little H plus and very little B minus. The bars are very small, but you have quite a bit of HB left over. So if you were to look at the beaker submicroscopically, you will see a few H pluses and a few F minuses in HF, but mostly you're going to see HF molecules floating around in solution. So weak acids are mostly molecules, very few ions in solution. Strong acids are no molecules in solution, all ions. Strong bases are just soluble hydroxide salts. So which hydroxide salts are soluble? Your solubility rules will tell you. First of all, it's the group 1s. All group 1 hydroxides are soluble. So this will give us NaOH, for example, that will completely split up to Na pluses and OH minuses, or potassium hydroxide, KOH, which is K plus OH minus. And those are the two that you're going to see most often. The other ones are quite rare, and so we won't bother to list those. But from group 2, you also have 3 soluble hydroxides, and they are calcium hydroxide, which will split up to give you a calcium 2 plus and 2 hydroxide ions. Strontium hydroxide is also soluble, and that will give you a strontium 2 plus and 2 hydroxides. And barium hydroxide is soluble, so that will completely split up to give you barium 2 pluses and 2 OH minuses. Well, that gives you some terminology and a basic idea of what's going on with acids and bases and how we know if something is an acid or a base. Next time we'll talk about concentrations And we'll also talk a little bit about how we know what the names for acids should be.